Good morning, students. I am Dr. Gauri Patil, Assistant Professor at Arts, Science and Commerce College, Ramananda Nagar, Burli. Students, in today's lecture, we will discuss about wave motion and ultrasonic wave. This chapter, which is from B.Sc. second year, paper number 6, Waves and Optics. Student, in last lecture, we have studied about the wave motion, what is mean by wave, what are the types of the wave, and how longitudinal and transverse waves are produced. In this lecture, we will discuss about the stationary waves on a string, means how stationary waves are produced on string and what are the normal modes of the string. So, dear students, look at this figure. So, students, what do you think of this diagram? Let me explain. Students, here there is a string of length L which is tied at both ends and some tension is given to it, and then we pluck it. When we pluck it, it starts vibrating, and when it starts vibrating, it has certain frequencies. Now when it is vibrating, it creates sounds, and when we listen that sound, from where that sound coming from. Okay, dear students, here this is the string and which having some length. Okay, and when we put some tension and we pluck at the center, by putting this finger at the center, we pluck this string, and because of this the string gets vibrating and the vibrations are looking like this. Okay, so here what happens, here is the air, means in this region there is in this region there is air, also in this region there is air. So when it goes up, the air is get compressed, means when the string goes up there is a compression, then rarefaction, again compression, and then again compression. Means same, when comes down, the air is again get compressed, means when this string is going down, then again there is a compression, then rarefaction, then again compression, and then again rarefaction. Means, so what happens, there are compression, rarefaction, compression and rarefaction. So means whenever there is a stationary wave formation, this stationary wave energy which creates energy in the form of longitudinal wave which comes to with our ear and we hear sound. Means, dear students, from this you got clear about what is mean by stationary waves and how stationary waves produce compression and rarefaction of air, and because of that there is a formation of longitudinal wave, and because of this type of energy which is produced by longitudinal wave which produces the sound, and because of that we can hear the sound of that vibrations. So students, now look at this figure. This is the standing waves. So what you notice from this is the standing wave which has the same wavelength and the frequency as the two traveling waves that make it up. Means here this is the string. This is the string and which is fixed at the both ends. So for given string, this is the string. Okay, this is the string and which is fixed at the both end. So what happens, when transverse waves travels from one end, then it reaches to the other end, and when two ends of the string are fixed, then the waves travel from one end and other end and get reflected back and travels in the opposite direction. Means here from one end wave is getting traveling and it reaches to that end, fixed end, and when reaches to this end, this wave is get reflected and then again come to the first end. Means there is a phase change of pi radians after reflection of the wave. Means when the wave, the traveling wave and the reflected back wave having the same frequency and opposite phase produce stationary wave pattern which is shown in the next figure. I will show that phase change in the next figure. Okay, so students, here figure A, this one is a figure A, and what it shows? It shows the undisplaced position of string AB along x-axis having length L. Okay, means this is the undisplaced position of string AB along the x-axis having the length L, and the two ends of the string are fixed at points A and B. Means the two ends of that strings at both points A and B, which are the fixed, and when the wave travels from end A, it reaches to the point B, and from it is reflected back. So here the wave is starting traveling, then it reaches to point B, and here it reaches to B, and then again it get back reflected, and then again it is come to another point A. So on reflection, a phase change of pi radiation, means how is the phase change? The phase change is a pi radiance which is introduced, and means because of that the trough in the incident wave is converted into the crest in the reflected wave. Means here this is the crest in the incident wave, and after reflection it is converted into the trough of the reflected wave. So because of that, there is a how much of phase change is there? There is a phase change of a pi radiations which is introduced. So these two waves form stationary wave pattern on the string, and which gives the nodes and the students. It is clear that when the particles of the medium perform simple harmonic motion with same frequency omega and having different amplitude A, which is function of x, then the fixed end points are always at rest, means their amplitude are always 0. Here look at this figure, and from this figure it is seen that these points which shows the nodes means no displacement, means here the amplitude is 0, and the points where the amplitude is maximum, which is called as the antinode. So students, in this figure all these points are the nodes, and these points where the amplitude is maximum, these points are called as the antinodes. So node is denoted by N and antinode is denoted by A. So here there are how many nodes and how many antinodes? So here there are 1, 2, 3, 4, 5 and 6 nodes, and 1, 2, 3, 4, 5 antinodes. So the nodes occur at distance which is the nodes are separated by distance lambda by 2, means always the distance between two nodes, successive nodes, which is separated by distance lambda by 2. Okay, and antinodes are also separated by distance lambda by 2, means this distance which is lambda by 2. Always remember that the nodes and antinodes which are separated by distance lambda by 2, means the particles between successive nodes are in phase, and during vibration the particles between successive node form a loop which is shown in this figure. So here the maximum points which are called as the antinodes, and the no displacement points which are called as the nodes. So students, it should be also noted that the length L of the string between fixed endpoints, which is integral multiple of lambda by 2, and then only well defined stationary waves which are observed here, means here in stationary wave all the particles perform simple harmonic motion with same frequency but different amplitude, means the amplitude at node is 0 which increases to maximum at antinode, means here this displacement is 0. Now first I will show you again in detail that I will repeat again that the amplitude at node is 0, means here amplitude is 0, and this amplitude is increases to maximum at antinode, and again it decreases to 0 at nodes in loop, means this is the one loop. So this amplitude here, this is 0, which is increases at antinode, then again decreases at node. So standing waves do not carry or transfer energy from one point to another point. So students, here there are the general expression for the normal modes of vibration of a string which is stretched under tension. Means here as we know that this is the string which having the length L. Okay, this is the string which having the length L and which is fixed at the both ends, and when this is stretched under tension, then this string is excited by plucking or striking. So here which type of wave is created? Here transverse wave is created, and whose velocity which we know, that is v is equal to under root t upon m. Means this velocity which is given by formula v is equal to under root t by m. Okay students, here the velocity v is equal to under root t by m, and v is the n into lambda, where n is the frequency of vibration and lambda is the wavelength. So students, here as you look at here, then what you observe, that here the length of the string is integral multiple of lambda by 2. Here this length which is integral multiple of lambda by 2, means here p which is equal to 1, 2, 3. First case there is first p is equal to what? P is equal to 1, means L is equal to lambda by 2. In second case, when there are two loops, then L is equal to 2 lambda by 2. In third case, there are 3 loops, L is equal to 3 lambda by 2. In sixth case, there are 6 loops and L is equal to 6 lambda by 2. This means when a string excited vibrates with different frequency which are integral multiple of some minimum frequency, which is called as the fundamental frequency. So higher frequency are also called as the overtones. Means the quality of sound is decided by the number of overtones which are present along the fundamental and their relative amplitudes. Means here there are 4 cases. Here we will discuss the 4 cases, means 4 modes. Fundamental mode, then second is first overtone. First overtone means second harmonic, then second overtone which is third harmonic, and fourth overtone means what? Fourth overtone is fifth harmonic, means first overtone, second harmonic, same like that, fifth overtone, sixth harmonic. So remember the difference between overtone and the harmonic. So students, here in the first fundamental mode, what happens there? As you know that in vibrating string, end points are always nodes, means here the end points are always nodes. So the simplest mode, there can be one antinode between two nodes. Here one antinode which is present between two nodes, and here length L is equal to lambda by 2, because we know that the two nodes are always at the distance of how much length? Lambda by 2, and here there is a one loop. And in second case, there are two loops which having the distance or which having the length L is equal to 2 lambda by 2, means L is equal to lambda. So similarly we get all the modes: fundamental, first overtone, second overtone, third overtone, fourth overtone, and so on. So students, we will explain in detail in the next slide. Strings. Here, as we know that the string of length L, which is subjected to the tension T and having mass per unit length M, vibrates with different frequency. Means here, this is the string which is fixed with both point and having length L. This is the length L of the string. And when we give the tension and having mass per unit, when we give the tension T, then there are the vibration with different frequency. So this gives rise to different stationary waves pattern, which are shown in this figure. There are different types of the different frequency pattern. First one, second one, third one, fourth one, and fifth one. So this first one is called as, this first one pattern is called as a fundamental or first harmonic, in which there is a production of one loop. This second one is called as a second harmonic or first overtone, in which there are two loops are there. In this third, which is called as a third harmonic or second overtone, in which there are formation of three loops. In fourth diagram, there are, which is called as a fourth harmonic or third overtone, where there are four loops are there. And in fifth, which is called as a fifth harmonic or fourth overtone, where there are presence of 5 loops. So dear students, these all are called as the normal modes of the vibration, and we show the first 5 normal modes of the vibration, but actually string vibrates with other higher modes also, and the resultant vibration is superposition of all these individual vibration modes. So as we discussed or as we derived in last lecture, that normal modes of vibration can be discussed by considering equation of frequency of string and wavelength. So we derive formula for the frequency of string, which is equal to n is equal to P upon 2L into under root T by M, and wavelength is lambda is equal to 2L upon P. These are the standard equation. So we will discuss about the 4 cases. First case means when P is equal to 1. Okay, P is equal to 1. So when P is equal to 1, then what happens? We have standard formula for the frequency of the string. N is equal to P upon N is equal to P upon 2L upon under root T by M, and lambda is equal to 2L upon P. If P is equal to 1, so we put P is equal to 1, then we get lambda is equal to 2L upon lambda is equal to 2L upon 1, which is equal to 2L. Okay, so the length of the wire is equal to L is equal to lambda by 2, and therefore N1 is equal to, finally we get 1 upon 2L into under root T upon M. Means when P is equal to 1, and when we put this value in this equation, we get this value. L is equal to lambda by 2 and N1 is equal to 1 upon 2L under root 2 by under root T by M. Now we consider the second case where P is equal to 2, then wave patterns developed on the string has length L and frequency N can be divided into 2 loops. Means when P is equal to 2. When P is equal to 2 means this case. When N is equal to, P is equal to 2. So we see the second case when P is equal to 2. We have standard formula, N is equal to P upon 2L under root T by M, lambda is equal to 2L upon P. So we put P is equal to 2 in this equation, we get value of lambda is equal to L. So lambda is equal to L. So by putting this into this equation, we get final value N2 is equal to 1 upon L under root T by M. Now next, third case. In third case, what happens? In third case, P is equal to 3, then stationary waves pattern develop is shown in figure 3. Which pattern? For 3? Yes. For P is equal to 3, this is the third pattern. So here, third case is, yes, this is the third case where P is equal to 3, then the stationary wave pattern developed is as shown in figure 3. The length is divided into 3 loops. So here we have standard formulas. N is equal to P upon 2L into under root T by M and lambda is equal to 2L upon P. We put value of 3, P is equal to 3 into this equation. We get lambda is equal to 3 by 2 lambda, and by putting this equation into this, we get N3 is equal to 3 upon 2L into under root T by M, which is equal to 3 and 1. So this mode of vibration is called as a third harmonic or second overtone. Now consider the fourth case. In fourth case, we get P is equal to 4. So when P is equal to 4, we put this value into this standard value, the standard equation. So we get value of lambda is equal to 2L upon P, means P is equal to 4. We put this into this equation. We get lambda is equal to 2 lambda. So by putting this value of lambda into N4, we get N4 is equal to 4 upon 2L into under root T by M, which is gives rise to 4N1, which is equal to 2N2. So this mode of vibration is called as the fourth harmonic or third overtone, or this is called as the second octave. So dear students, here we will stop here, and in the next lecture we will start with the next point, which is the derivation of equation, which is an alternative approach or for the group velocity and phase velocity. We will discuss in the next lecture about the group velocity and the phase velocity. Okay dear students, we will stop here. Thank you very much.